I'm Jonathan Tomkin from the University of Illinois. The climate is not fixed. Even before humans were altering the conditions for the climate, there was lots of variation. For example, 20,000 years ago, there was a global ice age. There was large ice sheets in places such as Canada, Scandinavia, Russia, and there were different distribution of animals around the world. So, for example, mastodons, a very large animal that's furry and adapted for the cold, used to live in what is the present-day United States of America. These changes were not caused by people. But we need to understand these changes if we're to figure out the changes that we're making, if we're to figure out how the changes that we're making are influencing the climate. So we need to look back before we can look forward. And one way we do that is by collecting data about previous climates. To understand the climate of the past, we need to collect data. There are two broad categories of data that we can collect. The first is instrumental data. So I have a picture here of a thermometer. We directly record the temperature. Other ways we might measure the climate include anemometers to measure wind direction and speed, tide gauges for sea level, rain gauges for precipitation. A second way we might collect data is by using what is known as proxies. This is known as proxy data. This is where we collect information from some natural process and we convert that into knowledge about previous climates. One way we can do this is with tree rings. If we measure the tree rings and their thickness, we can see if it was a good year for tree growth. So years in which trees grew well might indicate high levels of precipitation. Years in which trees grew poorly might indicate drought years. There are many other types of proxy data. These include ice cores, sediment cores, even coral cores, and also landforms and other observations. Instrumental data is very straightforward to interpret. We make a measurement and we know exactly what it means. Proxy data is harder to interpret and we have to make assumptions and we have to understand the natural world. One very important type of proxy data is ice cores. In this figure, a scientist is examining a piece of ice core drilled from Antarctica. And over the next few slides, I'll explain how we can use this information to look at the climate in the deep past. Unfortunately, we need to understand a little bit of chemistry first. Water is made up of molecules of H2O, two hydrogen atoms bonded to an oxygen atom. Not all hydrogen and oxygen is alike. For example, some oxygen is made up of 16 subatomic particles, which we might call oxygen 16, and some oxygen is made up of 18 subatomic particles, oxygen 18. Chemically, they behave the same. They bond with hydrogen and make water. But physically, oxygen 16 is lighter than oxygen 18. These two types of water then are known respectively as light water and heavy water. Imagine we're in a cold climate. Perhaps we're off the coast of Antarctica. The ocean is made up of both of these types of water. It has heavy water in it and light water in it. When the sun shines on the ocean, energy from the sunlight transforms some of this water into water vapour, and so it enters the atmosphere. Which do you think is easier to evaporate? A molecule of light water or a molecule of heavy water? The light water. It's lighter, you need less energy to lift it up. So if the climate is cool, more light water will enter the atmosphere than heavy water compared to when climate is warmer. The heavier something is, the more energy you need to move it. Keep that in mind. So this means in cool periods, the clouds produced from this evaporation have more light water than we might normally expect. So when precipitation falls out of these clouds, and of course since we're in a cold climate, for example like Antarctica, it falls as snow, we see that snow is what we would say is enriched in light water. In other words, it has more oxygen 16 in it than oxygen 18 than you would expect if the temperature was warmer. Because the climate is cold, there isn't enough energy to add too much oxygen 18 to that snow. So what happens then if we warm up the climate? The climate changes, it gets hotter. Well, we go through the same process. We're still in a polar region, but instead of being as cold as we were before, we're a little bit warmer. So there's more energy available to evaporate the water molecules. This means that it's easier to pick up those heavy water molecules, those water molecules that contain 18 oxygen atoms in them. So the water that enters the atmosphere and gets turned into cloud and then falls as snow has a different composition of heavy versus light water than during the cold periods. Now, let's consider, how does an ice sheet get built up over time? At first, the climate is cool, and so in this case there is less heavy water than usual. Perhaps the climate changes next. It gets warmer. This means we have a greater proportion of heavy water than we did before. And perhaps then we return back to our cold state, and so now again the snow falling has less heavy water. What's interesting is that different levels of ice in that ice sheet have different isotopic compositions. That is they have different compositions of 16 oxygen versus 18 oxygen, depending on whether the snow that fell to create that ice fell during the first cold period, the second warm period, or then the third period, which was also cold. Now, if we drill a core of this ice and extract it, we can measure the fraction of heavy to light isotopes and figure out whether or not the climate in the past, when that snow was laid down to form that ice, was from a warm period or a cold period. In other words, we can use these measurements to determine what the temperature of the ocean was that produced the snow that created the ice. It is the fraction of the light to heavy isotopes that tells us if the climate was relatively warm or relatively cold. So this is what an ice core looks like. There are yearly bands that fall from yearly snowfalls. The core section shown at the bottom is the deepest, and so has collected sediment from being close to the ground. And the cores also collect other sorts of information. The falling snow collects little bubbles of atmosphere, and these get trapped in the ice. As we saw in the reading, and we discussed in the previous lecture, if we have more greenhouse gases in the atmosphere, we might expect the climate to be warmer. Do we see that in the record? It turns out that we do. Here is some data from ice core taken from Antarctica. These two Antarctic ice cores, which are the blue and green lines, go back over 400,000 years. And in fact, there are some ice cores that go back twice as far as that. So these ice cores are giving us information hundreds of thousands of years in the past. There is a change in temperature for the blue and the green. So in other words, we're using this proxy data of this isotopic composition to derive changes in temperature relative to today. So in other words, if today is 0 degrees Celsius, so no change, periods at which have a positive temperature relative to that are warmer than today, and periods that have a negative temperature compared to that are colder than today. As a reminder, each degree Celsius is about 2 degrees Fahrenheit. So this graph goes from +3 to -6, so it goes from about +3 degrees Celsius is +6 degrees Fahrenheit, -6 degrees Celsius is -12 degrees Fahrenheit. That is relative to today. As we know from the reading, the Earth is currently in an interglacial, that is a warm period. And we can see that in this figure, we are currently at one of the warmest periods that has been seen in the last 400,000 years. There are only a few points in the past that were warmer than it is today. It is important to know that the climate has varied much in the past. That puts current climate change in context. It has been argued by some that the climate change we're seeing is natural. Scientists are concerned about the current climate change because the rate of change is much higher than is observed in these ice cores. Secondly, we're concerned because in these ice cores, as you could see in the readings, there is a clear correlation between the amount of carbon dioxide in the atmosphere and the temperature. As the level of carbon dioxide goes up, we see higher temperatures. For the first time in Earth's history, the climate is changing because of non-natural factors. In the next lecture, we will look at these non-natural factors and compare climate change today with climate change in the near future.
Produced by OCE Atlas Digital Media at the University of Illinois, Urbana-Champaign.